All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. So first of all, everyone, thank you for being flexible today and meeting online. So I will be back on Thursday, or my plan is to be back on Thursday. I do have a meeting on campus that I do have to be there for. So to this is just going to be for today. So thank you guys for doing that. How's everyone doing today? Right, doing good, I hope. Okay. Okay, so the plan for today, we have two more lectures this week, and then we have spring break. So what I wanted to do today was finish up. I think we stopped in the middle of an example last week on approximate solutions to weak forms. So we're going to finish up that example first thing today, and after that we're going to start our next section on finite element form. So basically, how do we take our weak form of a differential equation that we talked about last time and then turn it into a finite element problem? So how do we get element stiffness matrices, element forcing vectors, assembly, all that good stuff. Okay. All right, so a couple of reminders. Remember, ANSYS activity 2, along with all the MATLAB problems at the end of that activity, is due next Tuesday, so a week from today. So remember, the due date for that was pushed back, just because I know a lot of you are also taking the comprehensive exam this Friday. So, I wanted to give you a few days to work on the homework after that. So make sure you do that. And then your next homework assignment, I'm probably going to post it near the end of this week, even though, I usually don't like to have multiple homework assignments out. But with the spring break, I didn't want to wait until after the spring break to post the next homework assignment. So your next homework assignment will be posted, and that will be the last homework assignment, I think, for the class. Because then after that, I think is just the midterm exam and then the final project. And so when we come back from spring break, we'll discuss kind of the final project. We'll discuss the second midterm exam, a lot of that stuff. So, after the spring break is going to go pretty fast. We have a lot of things that we need to do to kind of finish up the semester. Okay. All right. And so I think that's it for my announcements. Are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and pick up where we left off. So actually, let me go back to our notes from last time. Okay. Okay. So this is the example that we were doing last time. And so basically what we were doing is we were taking our, example problem here. We have a rod that's being exposed to internal heating. And what we want to do is we want to find out the solution to this problem using the weak form. Okay. So remember, the main point of the lectures last week was that, for every differential equation, every boundary value problem, there are two different ways that you can express the problem. And so the first way is the strong form, which is kind of the standard way that we normally, that you've probably seen differential equations for in the past, which is given by, basically a differential equation like this, okay? And then what we can do is we can solve this equation. You've gone over methods for solving this equation before, okay? And then you can get your solution that looks like something like this, okay? Which is a function of the independent variable, from there. All right. So the other way that you may not have seen before in the past is a weak form solution, where you take your equation, you multiply by a weighting function, you integrate it, and you kind of do integration by parts. And so the point of doing this is to, kind of get the equation in a different form to kind of facilitate different types of solutions, okay? So the main type of solution that we're going to be looking at is approximate solutions to these equations, right? Because from the weak form, what you can do, right? So here's our weak form of the equations here, okay? From this weak form, what you can do is you can plug in kind of an assumed form, right? So you can assume a form of the solution beforehand, plug it into this equation, and then kind of get an approximate solution from there, okay? So that's kind of what we are in the middle of doing in this problem here, right? So we had our differential equation. What we said is that we're going to assume a quadratic solution. So we're going to assume that our solution takes the form of a quadratic function. So a naught plus a1x plus a2x squared, okay? Same thing for the weighting function. So the weighting function W is going to be B0 plus B1x plus B2x squared, okay? So we're assuming that off the bat, right? And so this is already kind of different from our strong form. But strong form, we don't assume anything beforehand. So for the strong form, we just kind of find the solution. But for a weak form solution, we're kind of making an assumption beforehand and then finding the best version of that function that solves to the solution. Okay. Okay. And so we were kind of in the middle of doing that. And so what we did from there is we applied our Dirichlet boundary condition. And so we applied our fixed temperature at x is equal to 0. And we found that A0 is equal to 0 and B0 is equal to 0. Or A0 is equal to 25 and B0 is equal to 0. Okay. And then we are in the middle of plugging in to our weak form equation here, right? So we had our first integral from 0 to L of dw dx times Ka times dt dx. Okay. Inside these derivatives here, we were plugging in our expressions for our functions. Okay, so w of x and t of x. Okay, and we had our body force term integral from 0 to L of wx s of x dx. Okay, and we're plugging in for w of x from there as well. And so after doing that, we end up with this integral expression here. So we have integral from 0 to 5 of b1 plus 2b2x, right? So this term right here, this came from dw dx, okay? And then we have a1 plus 2a2x. So this term here came from dt dx, okay? All right, so we're going to integrate that with respect to x. And then this b1x plus b2x squared, this was our weighting function w of x. Okay. Right. So what you've noticed here is that we've basically assumed a form for our solution and our weighting function. We've plugged it in. So now we're going to evaluate it because eventually what we want to find out, okay, we want to find out what the values of these two coefficients are, a1 and a2, because once we find a1 and a2, that's going to give us the rest of our solution. Okay. So let's use this equation. We're going to use this equation to solve for a1 and a2. Okay. Okay. So that's kind of where we were last time. Right? Any questions? Any questions on just any of this so far? This was just kind of a recap of last time. Okay. All right. So let's go ahead and perform. Well, let's FOIL this out first. Okay. So that's the first thing. So we're going to FOIL this out, and then we're going to perform the integration. Okay. Okay. But I'm going to do the foiling in a little bit of a unique way. Okay. So let's distribute the terms So let's distribute the terms in the first integral there, but I'm going to keep the b1 and b2 terms separate. Okay, so I'm going to have a separate b1 integral and a separate b2 integral. Okay. And actually, we can do the same thing for the second integral as well. So we can keep the b1, b2 terms separate for the second integral too. Okay. Okay, so for the first integral, b1 is just a constant, so we're just going to factor it out. Okay. So we have b1 integral from 0 to 5 of a1 plus 2a2x dx, okay, plus 2b2 integral from 0 to 5 of a1x plus 2a2x squared dx. Okay. This is equal to b1 integral from 0 to 5. Okay, so I'm just doing the same thing on the right-hand side integral of x cubed over 5 dx okay, plus x smaller, b2 integral from 0 to 5, x to the fourth over 5 dx. Okay. So all I've done there is I've just distributed the terms, but I've kept the b1, b2 terms separate, and you'll find out why in a second. Okay, so we did this just so that we can kind of just apply our normal kind of polynomial integration from here. Okay. Okay. So now let's evaluate all the integrals. Okay. All right. So if we do that, we get b1. We're going to integrate each term here. So we have a1 x plus a2 x squared. Okay. Evaluated between 0 and 5 plus we have 2b2 multiplied by a1 divided by 2 x squared plus 2/3 a2 x cubed. Okay. Evaluated from 0 to 5. Okay. This is equal to b1 times x to the fourth over 20 evaluated between 0 and 5 plus b2 times x to the fifth over 25, again evaluated from 0 to 5. Okay. Okay. So all I did in that step was just evaluate all of my integrals. Okay, so now they are all kind of evaluated. Okay, so now we're going to plug in the integration bounds. Okay. All right, so we do that. We get b1 times a1 times 5 minus 0, okay, plus a2 times 5 squared minus 0 squared, okay, plus 2b2 times a1 divided by 2 times 5 squared minus 0 squared plus 2/3 a2 5 cubed minus 0 cubed. Okay. This is equal to b1 times 1 over 20, 5 raised to the fourth power minus 0 raised to the fourth power, plus b2 times 1 over 25, 5 raised to the fifth power minus 0 raised to the fifth power. Okay. Right, so when you have the integration bounds, you evaluate every term of x at the upper bound minus every term evaluated at the lower bound, which is 0. Okay. Okay. So let's go ahead and simplify this. Okay. And so when we simplify this, we get b1 multiplied by 5a1 plus 25a2, okay, plus 2b2 multiplied by 25 over 2a1 plus 125 times 2, so that's 250 over 3a2. Okay. This is equal to 5 to the fifth divided by 20. So there's a factor of 5 on both the top and the bottom. And so this is going to be 125 over 4 B1, okay, plus 125 B2, okay? Because 25 is just 5 squared, so that's going to cancel out with 5 squared up top, and so that's just going to be, 125, which is 5 cubed, okay? All right. So we're in good shape here, right? So, when we started this, we wanted to get an expression. We wanted to find a way to use this equation to solve for the values of A1, A2, okay? So we have essentially two unknowns here, right? So we have A1 and A2. So that means we need two equations for it. And so how do we get two equations from one equation, right? So that kind of seems like it's magic. Well, let's look at these terms, and you'll kind of see why I grouped these terms the way that I did, right? So let me highlight this term in purple right here, okay? And let me highlight this one right here as well. And so if you look at those two terms, right, everything that I've highlighted in purple there is multiplied by B1, right? And so in order for this equation to be satisfied, right, in order for this equality to work out, okay, assuming that B1 and B2 are different, right? And so we're going to assume that, these are completely different variables. And so in order for this to work out, the things in purple on the left have to equal the things in purple on the right, okay? So in other words, we can make an equation out of this. So we can say that 5A1 plus 25A2 is equal to 125 over 4. Okay. We can do the same thing for the B2 terms. And so if we highlight these things in blue, and we can't forget about the 2, okay? Right? Everything that I've highlighted in blue there is multiplied by B2. Okay, so we can form another equation by it. Let's not forget to multiply the 2 on the left-hand side. Okay, so we have 25A1 plus 500 over 3 A2 is equal to 125. Okay. Right. So what we have here, from our one integral expression, through kind of clever use of the weighting function or the coefficients of the weighting function, we're now able to get two equations to solve for our two unknowns. Okay. Okay. So this is the purpose of the weighting function, and that's kind of why we use it in this weak form, right? Because the coefficients of the weighting function, we don't actually care what the coefficients are. So B1, B2 can be almost anything in this case, but the fact that they're different and the fact that that they can help us form this equation will let us solve for the coefficients of our solution function. Okay. And that's kind of where it gets the name weighting function, because what we usually use it for, as they were used those coefficients as weights, to form our different equations here. Okay. All right, so that's the purpose of the weighting functions, because now that we have the B1, B2 terms, we have two equations that we can solve for A1, A2. Okay, so you can solve this. It's a 2x2 system, and so you can solve this one by hand. It's probably not that difficult. Or you can solve it in MATLAB, whatever kind of floats your boat. Okay? And so our solution here is we have A1 is equal to 10, and A2 is equal to minus 0.75, or minus 3/4. Okay. Okay. So now let's plug this in. So now that we have all of our coefficients, we can form our final solution for T of x. Okay. Because remember, the way that we defined T of x was T of x is equal to A naught plus A1x plus A2x squared. Okay. We have A0, so A0 we found from our Dirichlet boundary conditions is 25. Okay. And then from the weak form of the equations, we now have the solutions for A1 and A2 as well. Okay. And so if we plug in for all this, our solution T of x is equal to 25 minus, or excuse me, plus 10x minus 0.75x squared. Okay. So this right here is our approximate solution to our boundary value problem. Okay. Okay. Remember, when we said about doing this, we weren't looking for the exact solution, right? This is not a strong form problem. What we're looking for is the best quadratic function that could get as close as possible to solving our boundary value problem. Okay. Because remember, the way we got this was we assumed a quadratic solution, and we went through this whole process, and we obtained the best quadratic solution. Okay. Now, is this the same as the exact solution? It's not, right? So if you remember from our strong form, okay, our strong form solution for T of x was T of x is equal to minus x to the fourth over 60 plus 25 over 3x plus 25. Okay. So obviously these two functions are different from each other, right? In our approximate solution, there's no x to the fourth term, which is kind of the key. Usually if you have a polynomial solution, the leading term kind of determines a lot of the solution here, right? And so because our approximate solution didn't have that x to the fourth, there's no way for this to be kind of the same as that one. Okay. But these are pretty close. And so if you were to plot these, our plots would kind of look like the following. And so, our exact solution, may look something like this. So this is like the exact solution. The approximate solution, may be, something like this. Okay. So not exactly the same, but but they try to overlap kind of as much as possible. Okay. All right. Any questions on this example here? Okay. All right. So one question you may be having right now is, why even bother doing this, right? So, if we went through all this trouble, to find a solution that's not even exact, right? So why even go through all this trouble? Well, for more complicated problems, for more complicated situations with more complicated geometries, 2D, 3D, things like that, finding the exact solution is a lot more difficult. As you kind of get to more and more kind of complex solutions, it generally becomes a lot more easy to find an approximate solution. Okay. And what we're going to do is we're going to take this to kind of the extreme. And so, we're going to go over how, we can take this framework, right? This framework of a weak form boundary value problem with assumed solutions and how we can turn this into a finite element problem, okay? So that's the next section we're going to go over, which is finite element formulations. Okay. All right, so we've seen what a finite element problem looks like, or at least we've seen the characteristics of a finite element problem through our direct stiffness unit. Okay. And through our direct stiffness unit, we've seen that, a finite element problem is characterized by a linear system of equations. Okay. Okay. And so the question that we're going to be trying to answer in this section is, can we find, or can we formulate the weak form of a solution in some way to get a linear system of equations, right? So we kind of did that already. So we kind of formed a linear system, in the previous example, right? That's how we solve for coefficients. But is there a way that we can kind of scale this up to kind of a more finite element process? So element stiffness matrices, assembly, boundary conditions, things like that. Okay. Okay. So the biggest difference that you'll see in this section when compared to the previous one is that, instead of finding a solution that spans the entire domain, right, which is kind of what we did in the previous couple of examples. What we're interested in instead is that we're interested in finding for approximate solutions that are only valid over a particular element. Okay? And so the difference is the following, right? And so in both strong and weak forms, we were finding a solution that's valid over an entire domain, right? Okay. So that T of X that we found, it's valid for the whole domain, right? So it's one solution for the entire one. Okay. But in FEA, right, in finite elements, and you've seen this in ANSYS, and this is going to become a lot more apparent from here, is that we have separate elements, right? And so if we take our domain and we mesh it, right? And so we kind of break this up into each of the different elements, right? So this right here would be our mesh. Okay. So this would be element 1, element 2, element 3, element 4, element 5. Okay. So we have a 5-element system here. What we're going to do instead is that for each of these elements, we're going to solve for a separate approximate solution. Okay. So for this element, we'll have T1 of X. This element here will have T2 of X. Okay. This element here will be T3 of X, T4 of X, T5 of X. Okay. And so our final solution from the finite element form will be just to kind of cobble or kind of paste together all these different elemental solutions. Okay, so that's the difference there. So it kind of seems like we're kind of doing some extra work here, right? But remember, a finite element algorithm or finite element method is meant to more be a computer algorithm, right? And so we want to kind of formulate this. We want to kind of express it in a way that a computer can kind of do, with a code like a method code. Okay. Okay. Any questions on this so far? Okay. So before we get into the methodology, we have to talk about the characteristics of the solution, or some of the requirements that these solutions have to go through. Okay? So since we're going to be solving for multiple solutions and multiple elements at the same time, there's some degree of continuity that has to occur between the different solutions. Okay? Because ultimately, what we want at the end of this process is, for all the solutions to kind of make one kind of nice contiguous solution. Okay. We want them all to kind of work together. We'll solve for each one kind of individually, but together they should form kind of one kind of big, nice picture. Okay. Okay. So what are these requirements? So the first requirement that we have is something called the continuity requirement. So the continuity requirement basically states that when you move from one element to the next, the solution should be continuous, right? So there shouldn't be any sudden jumps of solution between different elements. Okay. So this has to be true for obvious reasons, not only just for some solution kind of continuity and kind of smoothness of the solution, but also this is important for things like conservation of mass, conservation of energy, right? Just for that. Okay. So this kind of has one kind of important consequence here, which is the fact that, in order for the solution to be continuous across the elements, this means that, if you were to evaluate the solution at the nodes, right? The nodes are the points which connect the two elements together. The solution should be the same at the nodes between the two elements. Okay? Okay? So we're going to definitely make use of that fact when we're forming our systems of equations. Okay. All right, number two. Okay. The other important characteristic that your finite element solutions need to have is a characteristic called completeness. Okay. So completeness has to do with the mathematical form of the solution. Okay. So you already saw in the weak form that part of our solution procedure is to assume a functional form of the solution, right? And so that functional form has to have a certain, there has to be, there's some rules associated with it. Okay. Um, in particular for polynomials. And so, for our class, we're not going to do anything exotic. We're going to assume polynomial, approximate functions. Okay. And so for polynomial approximate solutions, a complete polynomial means that you should include all of the lower order terms, right? So of course, the order of a polynomial is defined by its highest order term, okay? But in order for the polynomial to be complete, you need to include all the lower order terms as well. Okay. And so you've already kind of seen this in our example, right? So for a quadratic function, okay, a quadratic function has a higher order term of two, right? So we have a second order polynomial. Okay. So not only do we need an x squared term, we also need a linear term, an x term, as well as a constant term, which has no x, right? So a0 plus a1x plus a2x squared. Okay. So we have to include all of those terms there in order to, in order for the polynomial to be complete. All right. So we're going to keep these in mind, as we kind of derive our finite element forms. All right. Any questions on this? All right, cool. Okay, so let's go over shape functions and finite elements in the next section. Okay. All right. So now that we know the requirements and kind of now that we know kind of what we aim to do, let's actually start deriving a solution. Okay. So we're going to start with kind of the simplest case here. So let's start with a two-node linear element with a piecewise linear approximation function. Okay. All right. So our element is going to look like this. Okay. So the x coordinates of the two nodes are going to be x1, x2. Okay. And we're going to assume the nodal solution values are going to be u1 and u2. Okay. So u1, u2 are the nodal solution values. Okay. So that should be a pretty familiar concept, right? So remember, back when we did direct stiffness method, we solved for the solutions at the nodes, right? So those were always going to be, those are always going to be, quantities of interest. Okay, U1, U2. Okay, X1, X2 are going to be the coordinates of the nodes. Okay, and so our approximate solution. Okay, our approximate solution in this case is U, we'll call it UE for the element, okay, of X is equal to, and we have a linear function here. So that's just going to be two terms. So we have A0 E plus A1 E X. Okay. And so just like we did with our weak form solution, the first example that we did today, our goal here is to find out, what are the best values for A0 and A1. Okay. So that's our situation, right? So this is kind of the simplest thing that we can do. So we have a two-node element, a linear approximation function, a linear approximate solution, and we're going to solve for those values. Okay. All right. So let's go ahead and solve this kind of the same way that we did before. Okay. But with the caveat, right? So our boundary conditions here are going to change. So remember the requirements that we have on this function, right? So we've already satisfied the completeness requirement, right? So we have a linear function and we included the constant term. So this polynomial is complete. Okay. The other requirement that this finite element function has to have is that it must be continuous across element borders. Okay. So I don't have it here, but you can imagine this element here is part of a greater geometry, right? So there's another element to its right and another element to its left. Okay. So the solution that we find on this element must be continuous with the solutions of its neighbors as well. Okay? And the way that we do that, or the way that we can enforce that, is that, since we're already kind of characterizing the solutions at the nodes, right? One way that we can enforce continuity is by forcing the approximate solution to match the nodal solutions. Okay. So essentially, we're going to be applying kind of two Dirichlet boundary conditions. So we say that the approximate solution when you evaluate it at x is equal to x1, it has to equal to u1. And the other requirement is that the approximate solution when you evaluate it at x is equal to x2 has to equal to u2. Okay. Okay, so let's go ahead and write those in mathematically, right? So that means u e of x has to equal to u1. Okay. Is equal to A0E plus A1E times x1, okay? But also UE at x2 is equal to U2 is equal to A0E plus A1E x2. Okay. Okay, so now we have two equations that we can solve for A0 and A1. Okay. So this is a pretty straightforward process, and so you can I think probably what I would do is I would subtract these two equations to eliminate A0, and then solve for A1 from there. Okay, and so basically what we get from this is that A0 is equal to x1 u2 minus x2 u1 all divided by x1 minus x2. Okay, and then what we get from A1 is that A1, both these have e's on them. Okay, A1e here is u1 minus u2 divided by x1 minus x2. Okay, and so if we plug these back into our approximate solution, we can get its value here. Okay, and so plugging into the approximate solution, we have ue of x is equal to x1 u2 minus x2 u1 all divided by x1 minus x2, okay, plus u1 minus u2 all divided by x1 minus x2 times x. Okay. So this right here is our approximate solution over our element. Okay. All right, so pretty straightforward so far. So this is kind of the same process that we kind of followed before. Okay. All right, so I'm gonna rearrange these terms a little bit just to kind of get them in a more convenient form. Okay. Because right now, this form here is not so convenient. So let's rearrange this. Okay. And let's rearrange it around our nodal solutions. And so what we should be able to do, right, is we should be able to group all the terms that are multiplied by u1 and group all the terms that's multiplied by u2. Okay. Okay. So let's go ahead and do that. Okay. And so if we go ahead and do that, so the u1 terms you can see are this term right here and this term right here. Okay. And so if we group those together, we get ue of x is equal to u1 multiplied by x minus x2 all divided by x1 minus x2. Okay. And then the u2 terms, we have a positive x1 u2 divided by x1 minus x2 and a minus x over x1 minus x2. Okay. So if we group those together, we get plus u2 multiplied by x1 minus x divided by x1 minus x2. Put a box around this one. Okay. All right, so this form is really interesting here. Okay, so if we look at these terms, in particular, we look at the terms that are in parentheses here. Let me define this. So let me call this a function n1. So this is going to be a function n1 of x. Okay. And this other function, we'll define it as n2 of x. Okay. So these end functions are pretty significant, and we're going to be seeing a lot of these over the next few weeks. Okay, so these end functions here are called shape functions. Okay. Another name for shape functions is called an interpolation function. Okay? Because what they essentially allow you to do is that they allow you to interpolate the solution within the element based on the nodal solutions. Okay, so eventually what we're going to be solving for is we're going to formulate this very similar to our direct stiffness problems, where we're going to solve for the solutions at the nodes, right? So we're going to solve for U1, U2. If you were interested in what the solution was going to look like or what it was in the middle of the element, you can do that using these shape functions. Okay. All right. One thing that you'll notice about the shape functions is that the order of the shape functions, or the polynomial order, matches the same order of what we assumed from the beginning. Okay, so these shape functions here are linear functions. Okay, so same as our assumed solution. Okay, and that's not by mistake. So that's perfectly intentional, right? So whatever order that you pick for your assumed solution, your shape function is going to match that order exactly. Okay. Okay. So we can use this information here and we can use it to form our element stiffness matrices. Okay. All right. So we will use okay. All right. Any questions on this so far? All right, cool. Okay, so before we jump to the finite element forms, let's do a little bit of notation. Okay. So since we're going to be forming matrices and vectors with these, it'd be nice to kind of put this in vector form. Okay. Okay. Since we have a distinct U1 term and a distinct U2 term, we can kind of group it together like this. Okay. So since UE of x is equal to U1 and 1 of x plus U2 and 2 of x. Okay. This kind of seems like it's a dot product. And so, let's go ahead and make use of that. Okay. And so if we make a vector n1 and n2, okay, so make it into a row vector like that. If we multiply by a column vector u1, u2, it would look something like that. Okay. All right. Another thing that we can do, just because it's going to be relevant pretty soon, is we're going to be taking derivatives of this with respect to x, right? And so if we have, let's say we take due dx, okay? The good news about this form is that U1 and U2 are simply just constants in this expression, right? So they're just the solutions at the nodes. And so any derivatives that we take, they're going to be put on the shape functions, okay? And so this is going to be U1 dn1 dx plus U2 dn2 dx, okay? So once again, we can put this in vector form. So we can make this dn1 dx, dn2 dx, all as a row vector, and then multiply by u1, u2. Okay. All right. In fact, before we move forward, let's write out the expressions for the shape function derivatives as well. Okay. So we know what n2 and n2 look, and n1 and n2, have these expressions up here. Okay. If you were to take the derivatives of these, you would get the following. Okay. So d n1 dx. Okay. We're going to take the derivative of our n1 function with respect to x, and so that's going to be 1 divided by x1 minus x2. Okay. And dn2 dx is equal to minus 1 over x1 minus x2. Okay. And so if you'll notice from these derivatives that the derivatives are constant, right? So x1, x2 here, those are simply just the coordinates of each of the nodes, right? And so their values are not changing. And so the derivatives are constant, which makes sense, right? Because our shape functions here are linear. And so the derivative of a linear function is just a constant. Okay. All right. So now that we have these expressions here, right? So we have our shape functions, our shape function derivatives, we have their associated vector forms. We can now plug these into our weak form. Okay. So let's write out the finite element formulations. Okay. And first thing we're going to do here, just like we did with direct stiffness, we're going to start by formulating the element stiffness matrix. Okay, so let's write out our weak form. So we're going to write out the weak form for 1D elasticity. Okay. All right, so our weak form looks like the following. So we have integral from 0 to L dw dx times E times A du dx dx is equal to integral from 0 to L of w of x, b of x, dx, plus any natural boundary condition, any Neumann boundary conditions. Okay, so we have w times a times t bar evaluated at our Neumann boundaries. Okay, so x is equal to gamma t. Okay. Okay. So this is the weak form that's applied over the entire domain, right? So this is from 0 to L. Okay. Remember, when we're doing a finite element formulation, we're only doing this for the specific elements. Okay. And so instead of integrating from 0 to L, right, for a particular element, okay, for a particular element, we're only integrating along the bounds of that element. Okay, so from x1 to x2. Another thing that we need to do, before we start plugging in here is we have the issue of the weighting function. Okay. And so for our weighting function, we're going to assume that it takes the same functional form as our solution. Okay. Same functional form, but different coefficients. Okay? So our W of x is equal to W1 and 1 of x plus W2 and 2 of x. Okay. All right. So we're using the same shape functions, right? And so that's actually going to be a really important point that we're going to make use of in a bit, right? So our weighting function has the same shape functions, just different coefficients. Okay. Okay. Um, another thing that we can have here is we can take the derivative of this as well. Okay. And just like our solution, our derivatives will be handled primarily on the shape function, or only on the shape functions. Okay. Oops. That, I don't know why I did that. Okay. And so when we take the derivative, we have dw dx is equal to w1 dn1 dx plus w2 dn2 dx. Okay. All right. And so they have their associated, vector forms as well, right? But just for the sake of brevity, I'm not going to write out the vector forms. Okay. So now that we've established all these things, let's go ahead and plug into our weak form here. Okay. So our weak form is integral from x1 to x2 dw dx times e times a times du dx, okay, is equal to integral from x1 to x2 of w of x, v of x, dx. Okay. All right. So for now, I'm going to ignore the Neumann boundary conditions, but we'll bring it back in a bit. Okay. Okay. All right, so let's plug in. So everywhere that we see W and everywhere that we see U, we're going to plug in our shape function representation. Okay. Okay. So dw dx here. Okay. We actually just have it up here, right here. Okay. So let's go and plug in here. And for du dx, we're going to plug in for this as well. Okay. Okay. So let's go ahead and do that. But I'm going to plug in their associated vector forms. Okay. And so their vector forms look like the following. So integral from x1, x2, okay, of vector w1, w2 times the column vector dn1 dx, dn2 dx, okay, So all this right here is a dw dx. Okay. These are going to be multiplied by E times A. Right? And so this is then multiplied by dn1 dx, dn2 dx, okay, times a column vector u1, u2, okay, dx. And so these two quantities right here are du dx. Okay. We'll come back to the right-hand side a bit later, probably, honestly, probably next class, because I just want to focus on the element stiffness matrix. And the element stiffness matrix is going to be this integral right here, okay? So we'll come back to you. Okay. So we'll see this guy. We'll see this guy on Thursday. Okay. All right. So if you notice, kind of one subtle thing that I did here is that for the vector form for dw dx, I swapped the positions of the which vector is the row vector and which is the column vector. So ultimately, you're taking the dot product between these two vectors, so it doesn't really matter which is which. But this form right here is a little bit more convenient because it allows us to get a matrix from it straight away. Okay. Okay. So from this form right here, what we can do, so because the coefficients here, W1, W2, U1, U2, these are all constants, they don't depend on X, we can factor them out of the integral. Okay. And so if we do that, we get W1, W2, that's kind of multiplied on the outside of the first integral. So you have W1, W2, okay. Integral from X1, X2 of dn1 dx, dn2 dx, okay, multiplied by EA, multiplied by dn1 dx, dn2 dx, dx, okay. All this is multiplied by the column vector u1, u2, okay. Okay. So what we have in the middle here, okay, I've put this thing in the middle here in parentheses, and actually let me emphasize this with some color, okay. And so what I have here is, if you actually do the vector matrix multiplication, right? So this first vector here is a 2 by 1 column vector, right? 2 rows, 1 column. And this other vector here is a 1 by 2, okay? When you actually multiply these two vectors together, it actually gives you a matrix, right? And that matrix there's no accident that we got a matrix there. And so that matrix is going to form our element stiffness matrix. Okay. So this integral right here, this is the basis of our element stiffness matrix for our finite element form. Okay. And so in fact, let me put it in another form here to make it a little bit easier to see. Okay. Okay, so we have an integral. So that integral is still there. So this integral is going to be from x1 to x2. Okay. We have our 2 by 2 matrix here. Okay. So our 2 by 2 matrix is dn1 dx times dn1 dx. Okay. Then we have dn1 dx, dn2 dx. Okay. And we have dn2 dx, dn1 dx, and then dn2 dx, dn2 dx. Okay, multiplied by EA dx. Okay. So that's the matrix that you get after you perform the vector multiplication. Okay. So you get a 2 by 2 matrix, and and we have the EA out in front. Okay, where each term in that matrix is a product of the shape function derivatives. Okay, so dn1 dx, dn1 dx, dn1 dx, dn2 dx, okay, and so on and so forth. Okay, so I think this one right here is good to box here. Okay. So this is our element stiffness matrix for a 1D elasticity problem. Okay. Now you might be wondering, how, you've probably never seen a matrix inside an integral like this, and so you may be wondering, how do I integrate a matrix, right? That seems kind of like a crazy thing to do. Well, the lucky thing here is that, the matrix, the integral is basically applying to every entry of the matrix, right? And so it's not like you're integrating the whole matrix by itself. You're integrating each entry in the matrix on its own. Okay? Okay? So it's not really any magic, it's something that you can easily do. So you just kind of integrate, integrate the matrix, or integrate each entry of the matrix. Okay? In fact, I will kind of give you the solution here to kind of the most common form, right? So in the most general form, we can't actually simplify any more than this, because the Young's modulus and the cross-sectional area, right? We're giving this problem flexibility where maybe the Young's modulus and the cross-sectional area are changing with x. Okay. So if E or A change with x, and so I think the most common case where you have a rod where the cross-sectional area is tapering along the rod. Okay, and so if those things change with x, you need to incorporate that into the integral. That needs to be incorporated into the element stiffness matrix. Okay. So usually if you have, A or E as some function of x, that gets incorporated into here. Okay. But the most common case is, maybe both E and A are constant. Okay. And so if the Young's modulus and the cross-sectional area are constant, then this just kind of pops out of the integral here. Okay. We already know, right? So we already know what the shape function derivatives look like. Those are also constants. Okay. And so if everything is a constant, you just have integral from x1 to x2 of dx. Okay. And so your integral then becomes x2 minus x1 multiplied by E times A multiplied by this matrix here. So dn1 dx, dn1 dx, dn1 dx, dn2 dx, dn2 dx, dn1 dx, dn2 dx, dn2 dx. Okay. So you basically just have a situation where you're taking a constant and you're multiplying it by the matrix. Okay. So this is if E and A constant. Okay. So that's all it is, right? So don't be intimidated by the integral of a matrix. It's a lot simpler than you think. Okay. So you just apply the integral to each term of the matrix individually. Okay. And then when we come back on Thursday, where we actually integrate the forcing term, the body force term, you'll kind of see that again. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all we got time for today. So thank you guys for coming today. So again, thank you guys for being flexible today as well. So I will be back on Thursday. So I will be in the class then. Thank you guys for coming. I hope you guys have a good rest of your evening, and I will see you on Thursday.